So today we'll be talking about threads. So we defined the thread before, and we said that the thread is a lightweight process or a sub-process. Okay, so a process may be divided into threads, and an application may be divided into multiple processes, and each process may be divided into multiple threads. So an application may be single process, single thread. It could be multiple processes, and each process is divided into threads. And it could be an application that consists of a single process, but that process is divided into multiple threads. Okay. And in this chapter, we will understand, the difference between multi-threading and multi-processing, or the difference between dividing an application into processes and dividing it into threads. There are some advantages in dividing an application into threads as opposed to processes. But many of the concepts that we will see here apply to both threads and processes. Some of the concepts apply to multi-processing and multi-threading. In particular, parallelizing a program and doing things in parallel as opposed to doing things sequentially. Many of the concepts here apply to multi-processing and multi-threading. So the main difference between multi-processing and multi-threading is that when you create a thread, that will take less time and it will take less additional resources. So threads are created within a process within one address space. So the threads within a process are within one address space. While when you create a process, you create a whole new address space with everything, data and code. It has its own data and code. While when you create a thread within the same process, you create multiple threads within the same process, they share the code and they share some of the data. So here, so this is a single threaded, this is multi-threaded. So each thread has its its own code, data, open files, stack, and registers. Now, when you have multiple threads, the threads are going to share the code and the data. Now, here data, what kind of variables are we referring to? What kind of variables does it make to share? Global. Does it make sense to share local?
Global and static.
Yeah, so in this section we have global and static variables. That's what makes sense to share between threads within the same process. Now local variables are on the stack. So it makes sense to give each thread its own stack. So each thread is going to have its own stack, but the global variables are shared. Now, sharing global variables is something that we will be taking advantage of in the next assignment. In assignment number 2, we will be using the fact that global variables are shared among threads within the same process to do fast communication, fast and cheap communication, without having to define a shared memory object. If you have these threads within the same process, within the same address space, and they share local variables, global variables, then they can simply communicate through these global variables. They all have access to the same global variables. So they can just share these variables. But of course, to do this properly, access to these global variables must be synchronized very well. Okay? Right. So in multi-threading, many applications these days are multi-threaded. Operating system kernels themselves are multi-threaded. And multi-threading can work well in many applications where you have a main thread that interacts with the user. So the user interface is in one thread, that interacts with the user, and then the actual processing of the tasks can be done in separate threads. And this works perfectly in a client-server architecture, or for the server in particular. It makes a lot of sense for the server. This is a server. It makes a lot of sense for the server to have a main thread that receives client requests. So this is client 1, this is client 2, this is client 3, and so forth. To have a main thread that is listening to client requests, and then if the processing of a client request requires a fair amount of computation, put it in a separate thread. So create thread number 1 to do the actual processing of client number 1's request, and create thread number 2 to do the actual processing of client 2's request. So the processing of these requests can be done in separate threads, while the main thread is still listening to client requests and still responsive to clients. So responsiveness is one important advantage of dividing a program into multiple threads. The thread that interacts with the user, we would like to keep it dedicated to interacting with the user or with the clients, and do the actual processing in separate threads. Okay. So these are the advantages of multi-threading. Responsiveness, which is what we have just explained. Scalability, which is taking advantage of a multiprocessor or a multi-core system. There is resource sharing, which is something that we talked about. Economy and speed. Now what's interesting about these 4 benefits is that 2 of them, responsiveness and scalability, can be achieved with multi-threading and multiprocessing. So you can get responsiveness by dividing the application into multiple processes instead of dividing it into multiple threads. And you can achieve scalability, which is taking advantage of a multi-core system or a multiprocessor system by dividing your application into multiple processes. But what's the advantage of dividing it into multiple threads as opposed to dividing it into multiple processes? The advantages are this resource sharing that we have shown. So resource sharing itself has multiple benefits. One benefit of resource sharing is that when you create a thread, you use less additional resources than if you create a process. If you create a process, you create a whole new address space. While if you create a thread, you create a thread within the same address space. So many of the resources are shared with other threads within the same process. Another advantage of resource sharing is that easy communication that we talked about through global variables. So if threads are going to share global variables, then they can just communicate using these global variables. And economy and speed, which means that when you create a thread, it's faster. So the system can create a thread faster because it's not creating a whole new process. It's just creating a thread within the same process. So there is less resources and less bookkeeping that the operating system needs to do, and less data structures, less operating system data structures to get created or updated. So it's quicker and it uses less resources. Okay. Now, something that we must emphasize here is that this scalability, or using a multiprocessor system or a multi-core system, there is no way that you can use or utilize a multiprocessor system without dividing your application into multiple threads or multiple processes. So, if you have one application and Okay. So if you have one application, and that application, so here is a big program, an application. And this application consists of a single process, single thread. Now, and you're running this on a single processor system, a computer with one CPU. Now, when you buy a computer with multiple CPUs, like a quad-core system or an 8-core system, this application is, assuming that the processors have the same speed, it's not going to run any faster on a quad-core system. So if, assuming that the processors on the quad-core are, have the same speed and the same power as the processor, the single processor. So buying a multi-core system is not going to make it any faster because the operating system is not magic. The OS is not magic. What does it mean? It means that it's not going to divide it into processes and threads for you. The OS doesn't divide your application into processes and threads for you. If your application is a single-threaded application, then the OS can run it only on one core. Okay? One of the purposes of this course is to understand what the operating system looks like from the inside and how the operating system is structured and what it can do and what it cannot do. And one thing that an operating system cannot do is dividing an application into multiple processes or multiple threads. So you, the application programmer, must do this, must divide your application into multiple processes or multiple threads in order to take advantage of a multi-core system. There is one thread, the system can only run it on one CPU. If there are 4 threads, the system, and you have a quad-core system, the operating system may be able to run each thread on a separate core. And then you will utilize a quad-core system. Okay? So this is a key idea. Now, another important concept is the concept of parallelism versus concurrency. What do we mean by parallelism and what do we mean by concurrency? Well, parallelism is the true parallelism where threads or processes are running physically in parallel, while concurrency is what we can achieve on a single CPU when we do time sharing. So a time sharing operating system that we have been focusing on since the beginning of this semester, it keeps switching from one process to another or from one thread to another. By the way, when there are multiple threads, when the kernel supports multi-threading, scheduling is going to be done at the thread level rather than the process level. So in this case, I have 4 threads, and the system is just switching between threads, thread 1, thread 2, thread 3, thread 4, then it's giving thread 1 another time quantum, and then thread 2, and so forth. Of course, here we're not showing the kernel time. So in this diagram, we're not showing the kernel time between threads, but in reality, there is kernel time. The kernel cannot switch without spending some time on the CPU doing context switching. But the point here is what we are achieving here with this switching on a single CPU is that we are allowing multiple processes to make progress. So the user will feel that multiple processes are making progress. The user will feel that these processes are running simultaneously, but they are not. They're not actually running simultaneously, because if you take a snapshot at any given point in time, here only one thread is running. Here only one thread is running. So if you take a snapshot at any given point in time, only one thread is running. So this is not true parallelism. But the user will feel that all of these processes are making progress at the same time because the system is switching very frequently. Here, you have a multi-core system. Now here the system assign each thread to a core. So threads 1 and 3 are assigned to one core, and threads 2 and 4 are assigned to another core. So in this case, we have true physical parallelism. So if you take a snapshot at this point, I have two threads that are actually running. So this is what we call parallelism. So parallelism is the real thing, while concurrency is switching between processes to give the user the illusion that multiple threads or multiple processes are making progress. Of course, there are other advantages of concurrency. And one of them is, for example, if one process or one thread runs into an infinite loop, then if one thread runs into an infinite loop, that thread will be wasting its own time quanta, but it will not be affecting other threads or processes. The system is not going to hang. So if a thread gets stuck in an infinite loop, that thread will be wasting its own time quanta, but it will not be affecting the time quanta of other threads or processes. By the way, in many of the concepts here, like I said, apply to both threads and processes. And that's why I may be using the terms thread and process interchangeably. Because this concept, for example, it applies to both threads and processes. The concept of parallelism versus concurrency. It's the same concept, whether you are dividing an application into processes or threads. Now, question. So this diagram implies that with a single CPU, it implies that with a single CPU, or it may imply that with a single CPU, you can never achieve real speedup. With parallelism, it's obvious that I can achieve real speedup because I can do things in parallel. Now, can I achieve real speedup with a single CPU? Can we achieve real speedup with a single CPU? Can we? Like if I have two threads, forget about four threads. I have two threads, and can doing concurrency achieve real speed up? Like if I, threads 1 and 2, thread 1 and thread 2, and I run them on a single CPU, and they take 10 seconds. It takes 10 seconds for both threads to complete if I execute them sequentially on a single CPU. Now, single CPU, but with concurrency or time sharing. Time sharing can achieve concurrency. So here, single CPU, no time sharing. Here, single CPU with time sharing. Can this run in less than 10 seconds?
No.
Well, the answer is yes. Why? It may run in less than 10 seconds. Why? Yeah.
It's just like the previous, the processes. If one of them needs I/O, then it doesn't hang up everything. It'll just hang up one thread.
Yeah, exactly. So it's the key is I/O. So here, I may get real speed up. So with time sharing, these may or may not. They may complete in 8 seconds. This is quite possible. Why? Because with concurrency, even though there is no real parallelism on the CPU, but there is parallelism that is happening between the CPU and I/O. So when T1 is running on the CPU, if T1 is doing I/O while T2 is on the CPU, then T1 may be making progress on the I/O device. So the I/O device is servicing T1. So T1 is actually making progress while T2 is utilizing the CPU. So if we execute them sequentially, when T1 needs I/O, then we will have to wait, everything will have to wait until the I/O for T1 is complete, right? But with time sharing or with concurrency, we can achieve that level of parallelism between CPU and I/O, and then we may get some real speed up. Even though on the CPU, at any given point in time, there is only one process on the CPU. But the CPU is one of many resources that a process needs in order to make progress. Okay? Questions on this?
Does this go back to what you mentioned in previous lectures about maintaining a balance in the type of process that's being run?
Okay, yes, great, yeah. So that's an excellent point. So if we have more balance between I/O and CPU, then we are more likely to get speed up by doing time sharing. So if you give me a CPU-bound process and an I/O-bound process, I'm more likely to get speed up. But if you give me two CPU-bound processes, I'm less likely to get speed up, because if both of them are CPU-bound, then they're going to be spending most of their time in the ready queue, waiting for the CPU, and they don't have much I/O to do. Same thing if both are I/O bound. If both are I/O bound, then they're going to be spending most of their time in the queue for the I/O device, and they will be spending less time on the CPU, or the CPU will be underutilized. So yes, with more balance, we can get more speed up. Okay. All right. So now with with multi-core, we focus on multi-core because many of today's systems are multi-core. But again, the concepts apply to multi-core processors or multi-processor systems that are the classical multi-processor systems where you have multiple processors on separate chips, not on one chip, like the multi-core. Now, in utilizing a multi-core system, we have some challenges. Like I said, the operating system is not magic. It's not going to divide a single-threaded application into threads. You have to divide it as an application program. And of course, there are libraries and programming language extensions that can help with that. So it's not necessarily you as a programmer. There are libraries and there are programming language extensions that can help you divide your application into multiple threads. But it's all at the application level. It's not at the operating system level. So the challenges here are dividing this application. And dividing an application, you may divide it into tasks that do different operations, or you can divide it into different pieces of data on which you apply the same operation. So, for example, you may have something like this. For loop A of I plus equals 5. And A is a big array. So A is a big array. B is another big array. Let's say times equals 4. Now this is a loop that does two different kinds of operations. So this is an add operation, and this is a multiply operation. So it may be possible here to put each operation on a separate thread. So to divide the program into two threads, thread 1 does the add and thread 2 does the multiply. So this is what we call task parallelism. Task parallelism. Another concept is data parallelism. If you do this, you have this and you have A of I plus equals 5. It's one operation, but you take this array A, this is A, and you divide it into 4 pieces, and each piece or each division is processed by a separate thread. This is thread 1, thread 2, thread 3, thread 4. So when you do something like this, which is something that we will do in assignment number 2, by the way. In assignment number 2, we'll have a big array and we will divide it into a number of divisions, and each division will be processed by a separate thread. This is what we call data parallelism. So here, task parallelism, each thread is doing a different task, a different operation, or maybe a different function. Here, data parallelism, where all threads are doing the same operation, but on different pieces of data, or on different divisions of the data that we are applying this. So these are the concepts. Now, in dividing an application into threads, we face challenges. The main challenge is dependency. Because if two tasks are dependent, then you will not be able to execute them in parallel, or to assign each one of them to a separate thread. So for example, if here we have, if this was A instead of B, okay, so now we are multiplying by 4 after adding 5. So these are dependent. And dependency prevents you sometimes from doing things in parallel, or at least it may complicate the parallelization of the code. So with dependencies, things become more complicated, and it becomes a challenge to parallelize execution. So you have to account for the dependencies. With dependencies, when you have dependencies, you may be able to divide your program into threads, but you have to do more synchronization. You have to do that carefully, because you have to synchronize them well so that all of these dependencies are satisfied and the execution is correct. Okay? So dependency is one challenge. Another important challenge is balance. If the threads are not balanced, if they are not doing about the same amount of work, or at least if you don't have enough significant enough work in each thread, you may not be able to get any speed up. For example, if you have two threads, one thread is doing, thread 1 is doing 90% of the work, and thread 2 is doing 10% of the work. In this case, you may not get any speed up. Things may end up being even slower than doing things sequentially. Why? So in this case, why may the overall performance of a multi-threaded version of this program run slower than the single-threaded version? So this is very much doing most of the work. Only little work is done here. But when you do multi-threading, you have to think about the overhead. So multi-threading doesn't come for free. So there is the overhead of creating threads and maintaining threads. So there is overhead in the system, and there is overhead at the application level in synchronizing these threads and making them wait when they have to wait, when they must wait for each other. So all of these kinds of overhead the time that is lost in the overhead may overweigh this small benefit. So here you only have a small benefit from multi-threading, right? So ideally, this is going to be, this will complete in 90% of the time. Right? So if the sequential, it takes 10 seconds, this will ideally complete in 9 seconds. But you will not get the ideal because of these all of these kinds of overhead. Now, testing and debugging is yet another challenge because debugging a parallel program is much more challenging than debugging a sequential program. And sometimes it's hard to reproduce a bug.